Are you able to see my PPT?
Yes, sir.
Audio is clear, na?
Yes, sir.
Okay. So in previous two problems, this is what just we want to summarize what we have considered in previous two problems. Velocity was a function of r only. Okay. So we have only one velocity component. There also we have only one velocity component. Other velocity component was 0. E, Z. Yes. Okay. Vz was non-zero, and Vx or Vr and V theta was 0. Only one velocity component. We can have this case also. We have one velocity. It can be a function of. Please mute your mic. Everybody, please mute your mic. Okay, Vz can be a function of r and z. So this is called as a, then you will get a two-dimensional second order differential equation. Here you will get a one-dimensional. Yes, Shubham. Roll number 91, 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 Shubham. Are you able to listen to me?
Your audio is coming to us.
Hello, sir.
Shubham, so you should mute your mic. If you want to tell something, just you tell me.
Hello, sir.
Yeah.
You call me. I joined late, sir. 5 minutes late.
Okay, but some of your mics are not mute actually when you are joining. You should make sure. If you have any questions, then you can unmute and tell me.
Okay, sir.
Okay, mute your mic, everybody. Okay, this is what we have case. So Vz, one dimensional velocity, is a function of r. So here what we will get? We will get a second order differential equation of velocity with respect to r. Second order differential equation of velocity with respect to r, and first order differential equation with respect to shear stress. Shear stress, first order differential equation of shear stress with respect to r, one dimensional differential equation. If say we have Vz, which is a function of r and z, then what we will get? We will get a second order differential equation of velocity two dimensional. One will be with respect to r and one will be with respect to z. So there will be a two-dimensional second order differential equation, velocity equation, and first order stress, first order differential equation of stress, two-dimensional, r and z. Similarly, if we have Vz is a function of r, z and theta, then certainly what we will be getting after getting a differential equation, we will be getting a three-dimensional second order velocity differential equation. Three-dimensional in a r dimensions, in z dimension and theta dimension, and second order differential equation of velocity. Now this we have seen. We have seen almost three problems we have solved. So how it can be solved? This can be solved by using two boundary conditions. These two boundary conditions are needed because I have second order differential equation, one dimensional second order differential equation. So two boundary conditions are needed to solve this problem. These two boundary conditions can be one flux condition and one velocity condition, or two velocity condition. This is also we have seen in last problem where we solved the problem using a concentric flow through annulus in concentric pipe. So two velocity condition we can solve and get the velocity profile equation. In previous two problem, flow over flat plate and flow through pipes, we have seen one flux condition is used and one velocity condition is used, and we got the velocity profile one dimensional. When we have one dimensional variation only, one dimensional variation, so we will get second order differential equation. Now if say we have one velocity component only, but it is two dimensional variation, so certainly what we will be getting, we will be getting second order differential equation of this velocity in r dimensions and in z dimensions. So how many boundary conditions are needed to solve this problem? Yeah, roll number 81. Roll number 81.
Sir,
Yeah, how many boundary conditions are needed?
4.
4 boundary conditions. What can be this 4 boundary condition? What will be this 4 boundary condition? So we will be needing 4 boundary condition. This 4 boundary condition, 2 will be of flux. Okay, 2 will be of flux and 2 can be of velocity condition. Or here not 2 velocity condition, it will be 4 velocity condition. 2 will be in r direction, 2 will be in z direction. So 4 velocity condition or 2 flux condition and 2 velocity condition. So I can solve the problem. So in all, here I will be needing 4 boundary condition. Similarly, if I have 3-dimensional equation, 3-dimensional, one velocity is there only in vz direction, but 3-dimensional equation. So I will be needing 6 boundary condition to solve this problem. Second order differential equation, 3-dimensional. So 6 boundary condition. This 6 boundary condition can be a 3 flux condition and 3 velocity condition. Okay, 3 flux condition and 3 velocity condition or 6 velocity condition. So to solve, if I have only one velocity and it is varying in all 3 directions, I will be needing 3 velocity condition. So now if I have velocity in all 3 directions, so if I have Vz, which is a function of r, z and theta, Vr, which is a function of r, z and theta, V theta, which is a function of r, z and theta, this problem can be solved using, at least I need a 18 boundary condition. Okay, 18 boundary condition. Out of these 18 boundary condition, okay, I can have 9 flux boundary condition and 9 velocity boundary condition. Then only I can solve this problem. But effectively, these are not 18 boundary condition. This will be only 6 boundary condition. But at every location, that component of the velocity should be verified. Okay, so I need a 2 location. At 2 location, velocity should be known, which all 3 component of the velocity should be known at 2 location. Or at 3 location, a flux should be known, and at 3 location, velocity should be known. Okay, so in all, so we can take, it will be a 18 boundary condition, and say you are solving unsteady problem. So Vz is a function of r, z, theta and time. Vr is a function of r, z, theta and time, and V theta is a function of r, z, theta and time. So again, so I need a Vz, Vr, V theta, one boundary condition with respect to time. So in all, considering all components, I will be needing 21 boundary conditions. Okay, 21 boundary condition to solve this problem, and there is no analytical solution available. Till now, there is an analytical solution available for a case like this only. I have only one velocity and it is varying in only one direction. In fact, many cases when we go for 2-dimensional second order differential equation, there is no analytical solution available. Many cases. Again, subjected to condition, some cases these are available, and this is not at all available, and this will be not at all available. So, so this velocity is very, very important. So how to get this? When I have all Vz, Vr, V theta varying in all three direction, and I have unsteady state problem. How to solve the problem? Anybody got any idea how to solve this problem? Here, rule number 1, Abhinav.
So by taking assumptions.
No, that taking assumption means we will reduce down to this form only. Without assumption, can it be solved?
So similar to that above condition that you have said, if two velocity conditions are known in all four directions in
Yeah. Okay, no assumptions. So I am considering Vz, Vr, V theta, and it is varying in all three dimension and unsteady state problem. Whether problem can be solved using any technique. As I am saying there is no analytical solution available till date.
experimental, sir.
Not experimental. Okay, experimental also people will do experimental and model fitting is there, and that is what we have seen in estimation of friction factor. Okay, estimation of friction factor and all. And secondly, it can be solved using numerical methods. That is why you are studying a numerical methods, and you might be studying a complete subject just to solve this kind of problem. And what is the name of that subject is computational fluid dynamics. The computational fluid dynamics is there na. So that is nothing but solving this equation when I have all three velocity and it is varying in all three direction. If I have unsteady state problem also, getting a velocity profile using numerical method. So whole subject is there. First of all, you need to study numerical methods also. Then systematic application of numerical method for solving this momentum transfer problem is nothing but the computational fluid dynamics. So whole subject is there. The day you will get an analytical solution for this, so complete numerical method will be less useful for you being a chemical engineer, and computational fluid dynamic branch this subject will be closed down the day you will get an analytical solution. So computational fluid dynamics is also very important. You can say continuation of transport phenomena is the computational fluid dynamics, where you cannot get an analytical solution, then you will go for numerical methods. So numerical systematic arrangement of numerical methods with some experimentally observed model incorporation and everything. So you will get all techniques in computational fluid dynamics to solve the momentum transfer problem. And that will be applicable for heat transfer also, that will be applicable for mass transfer also similarly. Okay. So this is what you can say compilation of all the information which we have collected from previous three problems. Okay, previous three problems are solved. So you are lucky, or you are lucky. So most of the time we will be stick to this case only one velocity and varying in only one direction, easy to solve. Only few cases are there where we will go for two-dimensional differential equation. Very few cases are there. So where you will get a two-dimensional, and this is not at all there in your syllabus itself. As soon as you will go, so it will be covered in advanced transport phenomena. Okay, any difficulty in understanding this? So that will tell you the importance of numerical method also. Subject numerical method you have covered, and again computational fluid dynamics also you are taking, very important subject. That is what very important from previous three problems and observation we can conclude the importance of all these subjects. Is it okay? Okay, then we'll move on to fourth problem. Okay, now this is two immiscible fluid. Okay, two immiscible fluid. So this is incompressible liquid fluid with viscosity mu1 and mu2 and density rho1 and rho2. So these are two velocities actually. Two velocities are there, two viscosity, two fluids are there. So using these two fluids, So have you taken down all the information from this problem? Yeah, roll number. So I need to ask specifically. Now general answer I will never get actually. Roll number 24, Bandi. Roll number 24, Bandi.
Hello,
Yeah. So what is given in this problem?
sir. Two fluids are flowing in a pipe.
No, not pipe. It is not a pipe. It is a pipe.
It's like flowing. Two fluids are flowing one over the other with a equal height, so that velocity flow rates are adjusted with the different densities.
So there are two parallel plates of length L and width W. Okay, there are two parallel plates of length L and width W. Okay, so this is one parallel plate. So this. This is upper parallel plate. And this is lower parallel plate. What is the distance between these two parallel plates? These are parallel plates. Okay. So what is the distance between these two parallel plates, Bandi?
2b, sir.
So this distance is 2b. This is 2b. What is the length of the plate?
L.
So this is the length of the plate. Okay. Where is the width of the plate? Bandi?
Width will be perpendicular to length.
Screen. Okay. Perpendicular to screen.
Yes,
Okay.
screen.
Okay, and this length and width is larger as compared to this distance between two parallel plates. This is given. Okay, length and width are very high. So this is length and this is width are very high as compared to a distance between these two parallel plates. Okay, and there are two fluids flowing. Two fluids flowing. One fluid is having density thing rho 1 and viscosity mu 1. Okay, mu 1. Mu 1 and other fluid is having density rho 2 and viscosity mu 2. Yeah, roll number 32, Lihas.
Yes, sir.
Where is the interface of these two parallel fluid?
The slit is half, means between distance from B from the plate.
Yeah, very good. So interface is set. Okay, so flow rate of this fluid and this fluid is adjusted in such a way that so interface is at the center. Okay, so distance, so upper fluid is rho 2, lower fluid is rho 1, and so this distance will be B, and this distance will be B. Okay. Now what do you think? Rho 1 is greater than rho 2 or rho 2 is greater than rho 1? Lihas?
So the fluid 1 is more denser, it's given, and the fluid 2 is less dense.
So rho 1 is greater than rho 2. Why? Because rho 2 is moving from the lower side and rho 1 is moving from the upper side, and there is an interface in between. Okay. And can you say something about mu1 and mu2? Can you say something mu1 and mu2? Rihas?
Sir,
Based on this information, given information, mu1 and mu2, whether mu1 is greater or mu2 is greater. Can you say something?
so mu1 is greater than mu2.
Why?
So because less dense fluid has less viscosity.
Who told you? Where it is written?
So, sir, I guessed it.
No, this will not be based on guessing. Na? Engineering will not work on guessing. What is your logic? What is the density of ethanol? Density of ethanol is 0.7. What is the density of oil? It is 0.8. Close to 0.8. So ethanol is viscous or oil is viscous?
So, oil.
So density is increasing, viscosity is also increasing. So what can you tell about this?
So then less dense liquid fluid will have more viscous.
No, it is less dense fluid will have more viscous. That is what I am given an example, na? Ethanol and oil. Oh, you are telling less dense fluid will have more viscous. How about water and oil? Then water density is 1, oil density is 0.8, and which is more viscous?
So oil is more viscous.
So can you justify from this thing actually?
So it's property of a material.
So we cannot just based on viscosity, we cannot tell anything on we just based on density, we cannot tell anything for viscosity. Okay, viscosity
Yes.
is a different property and density is a different property. Okay, so there is a relation density and viscosity, but it is not a kind of rule. Okay, it is not kind of rule that density is higher means viscosity will be lower or so. There is no rule based on this actually. So either mu1 can be greater than mu2, mu1 can be equals to mu2, or mu2 can be greater than mu1. Okay, anything is true. Anything is true. So what is the consequences of different viscosity actually? What is consequences of different viscosity? See, viscosities are different or viscosity is same. viscosity are different and viscosities are same, what is its consequences?
So on flux, the flux will be different.
Flux will be different. Okay.
Yes.
So here, say, which coordinate system will be suitable for you?
Our Cartesian.
Cartesian coordinate system. So where will be origin? Cartesian coordinate system.
So if we consider the plate from 0 to L, and
Okay.
it will be at the center, means at B.
Why
B
center?
distance from
Why
B
center?
distance from plate.
Why at center? Why at center?
So that it will be symmetrical for both the
Symmetric for the both the fluids. Okay,
yes,
now
both the fluids.
here actually one important information is there in this problem, that if two fluids are having different viscosity, these are handled as a different phases in momentum transfer. Okay, if two fluids are having different viscosity, these will be handled as a different phases in momentum transfer. So in momentum transfer, given two material are different phases and they will be different based on their viscosity. You can assume two immiscible fluid with equal viscosity, but they will be taken as a single phase in momentum transfer. In momentum transfer, there will be nothing change. Nothing will be changed from fluid 1 to fluid 2 if viscosities are same. So viscosity is an important property in momentum transfer that already we have seen. Viscosity is the important property in momentum transfer. Now viscosity is so important that phases are considered to be a different for two fluids if two fluids are having different viscosity. If two fluids are having same velocity, even if they are immiscible with a different density, they can be treated as a single phase and problem can be solved. Okay. Hence, we can take a origin. The origin can be taken at the center. So, say this can be my Z. Okay. This can be my Z. This can be my X. Okay. This can be my X. And y will be perpendicular to this. Okay. So for fluid 1, boundaries are from minus b to 0. X varies from minus b. So you can see this is minus b. So here 0, 0, and this will be minus b. So x varies from minus b to 0 is my fluid 1. Then x for fluid 2, x varies from 0 to plus b. And for both fluids, z varies from 0 to L and y varies from 0 to W. L and W are larger as compared to this 2b. As compared to B or 2b, L and W are very large. Okay. So this is very important. So roll number 62, Rameshri.
Yes, sir.
Just can you summarize what I told just now?
Yes, sir. We are taking the interfaces origin and 0 to minus b to the bottom plate and the 0 to b to the upper plate.
Okay.
And z varies from 0 to L.
Okay. When there will be a different phases and same phase in momentum transfer, when we consider a two-phase problem or single-phase problem in momentum transfer?
When there is different viscosity.
Yeah. So say consider an imaginary case. This is just an imaginary case. One oil is having density 1 gram per centimeter cube and it is flowing with the water 1 gram per centimeter cube, same density. Okay, density can be different. Say viscosity. Consider a viscosity of oil which will be equals to viscosity of water. Any imaginary oil you can consider of which viscosity is same as that of water, then momentum transfer you need not to take differently water and oil because their viscosities are same. So viscosity is the property which will be differentiating two fluids and which will be considered as the two phases in momentum transfer. Other property, don't worry about other property. Viscosity is the most important property. If viscosities are same, then it will be taken as a single phase problem. Okay. Roll number 67, Mayank. Roll number 67, Mayank. Roll number 83, Ishwari.
Yes, sir.
Okay. So what is your expectation of velocity profile? How velocity profile will be?
Was- Sir, first we have to take the boundary conditions, sir.
Huh?
Sir means we will get two boundary conditions, sir.
Okay. So what is
Means
expected velocity profile? How velocity profile will look like?
sir, it will be in parabola.
Parabola. So where it will be zero?
Sir, at the walls it will be zero.
Here it will be zero. Here it will be zero. Okay. Here velocity will be zero.
Yes, sir.
And where will be maximum velocity?
Sir, at the middle, sir, not middle. At one region, it will be maximum, sir.
So you mean to say upper region or lower region?
Sir, it will be upper region, sir.
Okay, in upper region. So it will go maximum like this. Okay.
Yes.
So this will be velocity profile. This is correct?
Yes, sir.
Okay. So anybody else? Why velocity profile is not like this? Okay, this will be zero and maximum velocity is at the center and then this will be zero here. So this will be maximum velocity. This will be this velocity. Or say I will draw here. So I will get maximum velocity somewhere in this case. And this is here. So this is say first velocity profile. This is say second velocity profile. And this is say third velocity profile. So you are saying only second velocity profile is possible. Ishwari?
Sir.
Okay. So everybody please write. So what do you think? Which velocity profile is correct? First, second or third? You can write in chat box. It is first, second or third. Second.
Excuse me, sir.
Just hold on.
Yes, sir.
What is written? 2. What is written? Second. Yeah, roll number 4, Aditya.
Yes, sir.
Very good. So what you have written?
Sir, we haven't specified the viscosity information.
Okay. So everybody is telling second. So what Aditya want to tell? Can you conclude, Aditya?
Sir, like if we are specifying the viscosity condition, then we can say which will be like I'm not telling in literal way, but which will be a little bit faster or which will be a little bit restricted flow.
Okay, very good. Can you just conclude your statement by explaining the thing? You are correct. It all depends upon viscosity.
Yes,
All
sir.
three cases are possible. Case 1
So
is
like,
also possible, case 2 is also possible, and case 3 is also possible.
in first case, if the viscosity one, if it is less viscous, then the first case will be correct. And
So you meant to say this mu1
less
is
than less than
less
mu2.
than mu2. Okay, mu1 is less than mu2. In second case,
Mu2 is less than mu1.
so mu2 is less than mu1. And when will be this third case possible?
Sir, as the both viscosities will be equal, there won't be two phases, so it will be symmetrical because we are taking origin at the center, so it will be equal.
Excellent, excellent. You are very much correct, and all other people are telling only second is correct based on whatever be the figure given in next slide. These are wrong. They are not understood what I told from a starting of the class. Starting of the class, I am explaining same thing. So if mu1 and mu2 is the property in momentum transfer which is differentiating material as a different phases. If mu1 is same as that of mu2 in momentum transfer, these two material will not be taken as a different phases. Consider oil and water with the same viscosity, imaginary case. So you can solve oil equals to water. You can solve oil equals to water and one fluid, and this one fluid filled between this hole and solve the problem if viscosities are same. If viscosities are different, then only this will be taken as a different phases. This will be handled as a different phases. And certainly now if mu1 is less than mu2, so it will offer a less resistance to this thing transfer. Okay, and flow is due to pressure difference. This pressure difference is same P0, and this is here you will have PL. P0 and PL. Flow is taking because of pressure difference. Flow is taking place because of pressure difference. So equal pressure difference is for fluid 1, fluid 2, every layer P0 and PL. Okay, so certainly if mu1 is less than mu2, less resistance to flow is offered by mu1 and there will be maximum velocity profile in phase 1. Here if mu2 is less than mu1, so less resistance is offered by mu2, phase 2 or liquid 2, and hence maximum velocity will be in phase 2. If mu1 equals to mu2, both is offering same resistance to flow, then you will get maximum velocity at the interface. At the interface. Okay, at the interface. So problem is symmetric. Problem is symmetric. So this is what expected velocity profile. Okay, it is good that you are just referring to next slide as you have, or you are referring to books, but you should understand also why it is so. Okay, why it is so. So these are the all three cases are possible. Okay, all three cases are possible. So this case I am erasing. This will be the case when you have mu1 less than mu2, and this case 3 will be for mu1 equals to mu2. Okay, when both viscosities are same, that time the problem is symmetric in x direction and maximum velocity will be at the center. Okay, all three cases are possible. All three cases are possible. So based on viscosity value, you will get these three cases. Okay, say for example, for this case, mu2 is less than mu1. So this is the case, say for example. Now what will be flux profile? What will be flux profile? Roll number 109, Sashank.
Yes, sir.
What is your expected flux profile?
Sir, at the flux will be maximum at the corners. At
Okay,
the
flux will be maximum at the corner.
Yes, sir. And it will be zero where the velocity profile is maximum.
So this will be there. Here it will be 0.
Yes, sir.
Okay. And upper part will be positive or lower part will be positive?
Sir, as it is given, the mu1 is greater. The mu1 is greater, so velocity will be lesser in the in the lower region. So the negative in the down part and the positive will be in the upper part.
Okay. So you mean to say like this? Like this?
Yeah, sir. Because viscosity is greater in the downward part, so viscosity velocity will be lower in this down region.
Why it is negative in upper part?
Sir?
Why it is negative in upper part and positive in why it is negative in lower part and positive in upper part?
Sir, I'm assuming that viscosity, as you have given, viscosity is more in the lower region. So
That is the reason. That is the reason.
Like tau equal to minus mu into dv by dx, no, sir.
Okay. So which is the important property which is deciding negative flux and positive flux?
The velocity, sir.
Velocity. It's velocity or gradient of velocity?
Gradient of velocity, dv by dx.
So you can see, so here flux is 0. So this will be a direction of momentum flux. And this
Yes,
will
sir.
be the direction of momentum flux. Okay. Now this is
Yes,
my
sir.
positive x-axis. So this momentum flux is in a direction of axis, positive axis. Okay, this is in x direction. This momentum flux above this line, the momentum flux will be in positive x direction, while below this line, momentum flux will be in negative x direction. That is why this is plotted negative. There is nothing to do with higher velocity, viscosity, velocity, nothing. Because above this, a momentum flux is in positive x direction. Below this, momentum flux is in negative x direction, which is shown by this pictorial representation. You can see, even though I am not giving you arrow, even though I am not telling this as a vector, because this is a tensor. This flux, momentum flux is a tensor, so I cannot represent it by arrow. I cannot represent it by arrow. So, but these are the pictorial representation. This is positive flux. This is kind of negative flux. Negative flux is indicating it is in negative axis direction. It all depends upon location of axis. Okay, location of axis. If I take it here, so everything will be negative. Okay, so it will change altogether. Okay, so it all depends upon this. Okay, everybody understood this? Roll number 114, Yuvraj. Hundred and 14, Yuvraj. Roll number 112, Sricharan.
Yes, sir.
So which velocities are zero and which velocity are non-zero?
Sir, non-zero in the z direction, sir,
So Vz
is non-zero.
is not zero. Vx,
Vx will be zero.
why?
Vy also zero, sir.
Why?
Sir, because velocity is varying only in the z direction.
Velocity is varying only in z direction.
in x direction with respect to
Velocity
x.
is varying only in x direction.
Yes,
You
sir.
are telling Vx equals to 0. So you should know why there will be velocity in any case. Being a chemical engineer, these are very important. Why there will be velocity? There should be some driving force. Okay. There should be
Yes, sir.
some driving force for velocity, na? Then only molecules will move.
Yes,
And
sir.
what is the driving force in momentum transfer?
Velocity gradient.
Velocity gradient is a driving force in momentum transfer. For velocity, I am telling. That is for momentum flux.
Pressure difference.
Pressure difference. So what is the pressure difference in x direction?
Oh, rho g into height from point rho g into h rho g into x plus delta x.
X plus delta x. Pressure difference in x direction.
P naught minus into
X
P
direction.
naught minus PL minus P naught.
X direction. That is x direction. You are really into class or you are doing something else?
Sir, into class only, sir.
So what is the pressure difference in x direction? Which is my x direction?
Sir, x direction is upwards.
Upward. So what is the pressure difference? Total pressure difference in x direction. So x starts from this point, lower plate to upper plate. What is the pressure difference?
So P naught minus PL by L. Sir, maybe no pressure difference in x direction, sir.
Sri Charan, you are telling that sometime your name is Sri Charan, sometime your name is something. Is it the case? Okay, your name is Sri Charan, your name is Sri Charan. Now you are telling that there is a pressure difference P0 minus PL divided by L. That is the pressure difference in x direction.
Z direction, sir, not in
What is the
x
pressure
direction.
difference in x direction?
No pressure difference, sir.
Why?
Sir, B is very small.
Very good, very good. Because 2B is very small. A distance, these layers or layer of the liquid is very small as compared to width and W. Okay, this is true only for smaller value of B. So there is no much pressure difference in this direction. That will give like there is no driving force in x direction for velocity. Hence Vx equals to 0. Why Vy equals to 0? Sri Charan?
Sir, similarly, there is no pressure difference in y direction also.
Very good. There is no driving force in y direction. So now Vz can be function of x, y, and z. Roll number 103, Saurabh.
Yes, sir.
Whether Pz, Vz is a function of x, y, or z.
It's a function of x.
Okay, Vz is a function of x. Why? Why it is not function of y?
Sir, in the y direction, we can say it's symmetrical.
Symmetrical.
Sir,
I will give you reason. End effects are neglected. Now you tell me how.
sir, and okay, sir. The in the y direction, we are saying there are no driving forces. So only effect that will change the velocity profile in the y direction will be the end effects that will change the boundary velocities. But we are assuming that end effects are neglected, so the velocity profile will be
End
constant.
effects are neglected because W is very large as compared to 2B. This is specific reason because width is very large as compared to 2B. When width is large, then only I can tell end effects are neglected. Okay, so this is not a function of y.
Okay.
Whether it is function of Z?
No, sir.
Why?
Continuity equation.
Okay, continuity equation and end effects are neglected.
Yes.
So why it is a function of X only? Can you just justify?
Sir, because there is viscous forces in between the layers of liquid in the X direction.
No, reason is at the wall there is a velocity 0 and there is some velocity at the intermediate when I am moving in X direction.
Yes, sir. Yes, sir, the velocity at the wall is 0 that because of the viscous forces, right? Because they are acting in
Slip
between
condition,
them.
no slip condition, no slip condition. Yeah,
Yes, sir,
viscous forces also.
that is only derived from that due to viscous forces.
Yeah, okay, okay. That is called as a no slip condition.
Yes.
So at the wall, velocity is 0, and as I am moving in X direction, a fluid is attaining some velocity. When I am
Yes.
moving in X direction, fluid is attaining some velocity under the influence of pressure difference. P0 minus PL divided by L. Hence, velocity is a function of X only. Velocity
Yes.
is a function of X only. Velocity Vz.
Vz is function of X only.
Vz is a function of X only. So, which momentum balance equation I will be using? First will be X momentum balance, another will be Y momentum balance, third will be a Z momentum balance. Momentum balance, a shell balance for Z momentum, shell balance for X momentum, shell balance for Y momentum. Which momentum is important here?
Sir, only in X direction.
X momentum you have.
No, sir. Only Z direction. The momentum velocity in Z causing the momentum in X direction. So we will take it in X Z direction.
Only Z momentum is important. Okay, only Z momentum is important. So what are the three components of momentum you need to consider?
Sir, it will be tau's. Sorry. We are taking velocity in the velocity in Z direction causing momentum in X. So tau XZ, tau YZ, and tau ZZ.
Very good. Tau not tau. We will start with phi.
Yes, so phi.
Okay, phi XZ. Okay, phi
YZ.
YZ and phi ZZ. So what is phi XZ equals to?
So phi XZ will be equals to pressure P.
No.
Sorry, P will be 0.
Directly. Tau XZ. Tau XZ.
Tau XZ plus rho Vx Vz.
Very good. Vx Vz. Why P is not coming in here?
So because I is not equals to J.
Very good. What will be this phi ZZ equals to?
Tau YZ plus rho Vy plus V into Vx.
Tau YZ plus rho By
To Vz.
Vz. Okay. Just I will write this phi ZZ here somewhere. Phi ZZ. Phi ZZ equals to
P
plus
tau ZZ
tau ZZ
plus rho Vz square.
plus rho Vz into Vz. Okay. Okay, roll number 86, Prashant.
Yes, sir.
Can
Hello.
you see this phi XZ?
Yes, sir.
First of all, tell me what will be the dimensions of differential shell?
Sir, differential shell will have length L, width W, and thickness delta X, sir.
Very good. Why delta X only?
So because of velocity Z component, Vz is varying in x direction only.
Very good. So what is the gravitational force acting in the direction of flow?
Sir, along the direction of flow, sir, gravity will be zero, sir.
Very good. So there is no gravitational force acting in a direction of flow. It is given that it is horizontal.
Thin slit. Yes, sir.
Horizontal. Flow is horizontal, and this will be my G. So this will be my G. So in the direction of flow, it will be 0. Okay, Gz equals to 0. Okay, Gz will be equals to 0. So need not to take, because I am taking Z momentum balance equation. Z momentum balance equation. So this is clear to everybody. There is no gravitational force acting in a direction of flow. Okay. So what about this phi xz? Prashant?
Yes, sir. So
Tau,
phi,
tau
sir,
xz
tau, sir,
0
tau
or
xz will be non-zero, sir.
non-zero, and this is?
So this will be zero because Vx is zero.
This is 0. How about phi zz?
So phi zz.
Yeah, this is phi yz.
Yes, sir. So phi yz will be, sir, zero, sir.
Tau yz is 0, and this
Yes,
is
sir.
0. Very good. And how about phi zz?
Sir, phi zz will be p into, sir, that chronicle delta will be 1 plus rho vz plus tau zz.
Tau zz, what will be the value of tau zz? 0, non-zero.
Sir, tau zz will be zero.
Very good. So this will not be there. So you need to consider this term, this term, this term. Okay. And what is the this thing actually? So now so what is the area perpendicular to phi xz? Okay, let it be. Roll number 78, Deepak.
Yes, sir.
What is the area perpendicular to phi xz?
Okay. Sir, it's W into L.
W into L.
Yes.
What is the area perpendicular to phi zz?
Phi ZZ. Mm, W into delta X.
Very good. Will be a W to delta X. So what is the momentum in coming in my differential shell? This is my differential shell. So say consider this is my differential shell. Okay, this is my differential shell. So this is my differential shell. L W into delta X. Okay. So what is the rate of momentum coming in my differential shell in X direction?
In X direction.
Yeah. Coming in my differential shell in X direction. I am
Yes,
talking
sir.
about Z momentum only. Z momentum coming in. So this direction I am talking about.
Yes, sir. So it will be phi. Just a second. Phi at Z equals to 0. First,
Which phi? Z equals to 0.
Yes, sir. For the in, right? We are calculating for
this arrow. Can you see this
okay,
arrow?
okay. Yeah. Got it.
In X direction.
Mm-hmm. So it will be tau xz at x equals to 0.
Not tau xz. Phi xz.
Sorry, phi xz at x equals to 0.
X equals to not 0.
X equals to
x
yeah. And another one will be x plus delta
minus phi
x
xz
at
at
x equals to x plus delta x.
x plus delta x. This is in x direction plus. Now this is 0 actually. This is 0. So you need not to consider this. Phi yz you need not to consider. But
Yes.
phi zz. Now this arrow is considered and this arrow is considered. Going out is considered. Now phi zz, z momentum coming in my differential shell in z direction. So here this.
That's it.
What will be this?
At z equals to 0.
Which phi?
Phi zz at z equals to 0.
Phi zz at z equals to 0
Yes, sir.
minus
Phi zz at z equals to L.
phi zz at z equals to L, that is equals to 0. Okay?
Yes, sir.
Because there is no gravitational. So here rate of momentum coming in my differential shell in x direction. Rate of momentum going in my different into WL, okay, into area. So this will be into area. This will be into area, W into x, okay, into area. So this will be rate of momentum coming in. This will be rate of momentum going out in x direction. This will be rate of momentum coming in. This will be rate of momentum going out in z direction. There is no generation and consumption of momentum because there is no gravitational force acting in a direction of force. Okay, in a direction of flow. So this will be equals to 0. Now substitute this phi xz and phi zz here. Okay, this is phi xz and phi zz and rearrange the equation. And this value rho vz will at z equals to 0 will be equals to rho vz at z equals to L. So and you divide it by L W delta x, L into W into delta x, and take delta x tends to 0. So you will get a differential equation here. D by dx of tau xz. D by dx of tau xz will be equals to P0 minus PL divided by L. This is what you are supposed to get. Okay, just rearrange the equation. Rearrange the equation and get the equation. Differential equation of a momentum flux. Differential equation of momentum flux. Rearrange equation. Rearrange the equation. Anybody? Okay, because of this online writing and everything, so it might be confusing just if you see slide once again. But if you are following step by step what I am discussing till now, everything is clear on this slide actually, how to get this differential equation. If anybody is getting any problem in this momentum balance, can we say as density of two, viscosity will be higher for one. Roll number 83, Ishwari. Ishwari.
Yes, sir.
So you are correlating density with velocity. Actually, you have written something in chat box.
Yes, so when we were discussing about the velocity profile, sir.
Yeah, but that is not velocity. Magnitude of velocity is governed by resistance to velocity is a viscosity, not density.
Okay, sir.
Okay, density has role to play, but that can be neglected for time being. That effect of density on velocity is not that much high. Okay. Currently, we are into say introduction to momentum transfer, and viscosity is the major property which is playing role to decide the velocity. Viscosity. Okay. Density is for timing. You can say nothing to do with that.
Okay, sir.
So everybody is getting this momentum transfer. Okay, this is what this thing is there. Everything we have discussed actually. This will be a plane of zero shear stress. So here it will be a positive, here it will be negative. This positive sign indicates shear stress is in x direction. This negative sign indicates shear stress in this is in positive x direction, this is in negative x direction, and origin is taken here. For this problem, there are in fact 12 options of origin. Okay, 12 options of origin are there. Okay, so you can have two origin here, two origin here, two origin here. These are 6 origin at z equals to L, and again 6 origin at z equals to 0, and again 2 origin here, 2 origin here, 2 origin here. There are 12 options of origin, and you can solve the problem using any origin. Only the thing is you will get a different model equation. You will get different model equation, different profile equation, that's all. Otherwise, absolute value will remain same. Interface will be at the center, but if you take the origin here, so that we'll discuss afterward. First, do the shell balance for here. So you should be getting this equation: d by dx equals to p0 minus pl divided by l. Adjust negative sign also, p0 minus pl divided by l. Just let me know if anybody is getting this equation. After doing shell momentum balance, you should be able to get this equation. Okay, very good. Very good. Any difficulty in understanding how to get this equation? Why gravitational force is not into picture? Here pressure is just a pressure given by external agencies like pump and all. Okay? So this pressure gradient is created with the external agency. No gravitational force is neither supporting the flow, neither opposing the flow. Anybody is not getting this equation? Everybody is getting this equation? Okay, now most important thing. Everybody is getting this equation. Anybody has any difficulty? Most important thing now, I got a shears momentum balance equation. But here I have two phases. This is phase 1 and this is phase 2. Why these are two phases? Because viscosity of compound 1 is different than viscosity of compound 2. Viscosity is the property which is differentiating two material as a different phases in momentum transfer. So based on which property will be differentiating two material as a different phases, it is viscosity. Because viscosity 1 and viscosity 2 are different. Here viscosity mu2 is less than mu1. Hence this is phase 1, this is phase 2. So I cannot use same shell balance equation for both the phases. So I need to use this shell balance equation for phase 1 separately and this shell balance equation for phase 2 separately. Okay, so this equation for phase 1 will be a d by dx of tau xz for phase 1 will be d by dx, that will be equals to p0 minus pl divided by l, and this will be d by dx of tau xz for phase 2, that will be equals to p0 minus pl. Okay, it means that for this region, okay, for this region I will have different profile equation for flux. For this region I will have different equation for profile for this momentum profile. Okay, momentum flux profile will be different in phase 1 and momentum profile will be different in phase 2. These are governed by two different equations. These are governed by two different equations because phase 1 and phase 2 are having a different viscosity and they behave differently in momentum transfer. Okay, now when I have, you can say Vz. Okay, Vz is a function of x. How many boundary conditions are needed to solve this problem? Here, roll number 66, Aryan.
Yes, sir.
How many boundary conditions are needed to solve this problem? Vz is a function of x.
Sir, first of all, we need fluid one.
How many boundary conditions? First of all, tell me whether 1, 2, 4, 10, 9, how many boundary conditions are needed?
2, sir.
2 boundary conditions are needed.
Yes, sir.
Okay. So this is already discussed and everybody understood this.
Yes, sir.
Everybody understood this. If Vz is a function of x, so I will get a second order velocity differential equation, one dimensional second order velocity differential equation 2. This can be solved using one flux boundary condition and one velocity boundary condition, or this can be solved using two velocity boundary condition. Okay. Now I have two phases. So Vz for phase 1 and Vz for phase 2. These are two phase problem. This is function of Vz for phase 1 is a function of x and Vz for phase 2 as a function of x. How many boundary conditions are needed to solve this problem? Yeah, Aryan.
Yes, sir. One boundary condition.
Oh, so you can solve this problem using one boundary condition.
No, sir. Means fluid and solid fluid both.
I am asking number of boundary conditions needed to solve this problem.
2, sir. Total 2 plus 2 4.
2 plus 2 4 or 2 minus 2 0?
No, sir. 4.
4 boundary conditions are needed.
Yes, sir.
Okay. So what can be this 4 boundary condition? First
Sir,
of all, if I have, don't worry about this problem first of all. This problem can be solved using 4 boundary condition if I have 4 velocity condition. This is velocity, 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 velocity. 2 for this velocity 1, 2 for this velocity 1. Then second case, when this problem can be solved. Roll number 40, Ravi.
Yes, sir.
So to solve this problem, so this problem can be solved using 4 boundary condition. I needed 4 velocity condition,
Or two flux for a fluid one and two flux.
Okay, 2 flux condition and
Or
2
two
velocity condition. This
velocity.
problem can be solved, or any other case is possible. So this will be solved if I have one flux condition and 3 velocity condition. This problem can be solved. But problem cannot be solved if I have 3 flux condition, okay, and 1 velocity condition, or 4 flux condition. Okay, this is 4 flux condition. This problem cannot be solved. Okay, just now I explained same thing, because I am hitting first order differential equation with respect to flux and second order differential equation with respect to velocity. So problem can be solved using 4 velocity condition, or 2 flux condition and 2 velocity condition, and 1 flux and 3 velocity condition. How many boundary conditions are available? Now just take down information from problem. So whether boundary conditions are given. Roll number 15, Sai. What are the boundary conditions given in a problem? Sai, not able to listen to you. Roll number 1, Abhinav.
Yes, sir.
Yeah. So what are the boundary conditions given in this problem? Whether 4 velocity conditions are given, or 2 flux condition and 2 velocity conditions are given, or 1 flux and 1 velocity conditions are given.
Sir, 1 flux and 3 velocity conditions.
Very good. What are these boundary conditions? Can you just write it mathematically? Can you tell me mathematically?
So no slip condition, that is at x is equal to b, we can say
X
v.
equals to B.
Yes, sir.
No slip condition.
Yes, sir. That is velocity condition.
Modified no slip condition. What is that? You are telling x equals to B means this surface.
Yes, sir.
Okay. So what is that?
Velocity is 0.
Which velocity?
Vz.
Vz, and for phase 2.
2. Yes.
Phase 2 equals to 0. This is one velocity condition. What is another velocity condition?
At x is equal to minus b, Vz phase 1 is 0.
At x equals to minus b, Vz
phase
for
1
phase 1, that
is
is
0.
equal to 0. Okay. Then
At x is equal to 0,
x equal to 0,
Vz is equal to 0. Vz at phase 1 and 2 are equal to 0.
Vz for phase 1 will be equals to Vz for phase 2. This is modified no slip boundary condition.
Yeah.
Okay. And fourth condition?
At maximum Vz, stress will be 0. Means tau will be 0.
But where it is? What is this distance at x equals to?
So we can take lambda x, or
Yeah, that will be very complicated, but fourth boundary condition is already given. It will be similar to continuity of velocity at x equals to 0. So at x equals to 0,
both will be equal, means tau.
continuity of flux, tau xz
For phase 1 is equal to
phase 1 will be equals to
tau
tau
xz
xz
phase 2.
phase 2. Now I have, this is not needed, this is also not available, this is available. So this problem can be solved. So overall, so I can say that, okay, everything is given and this problem is solvable. There is nothing hidden or nothing not given, so that I can I cannot solve the problem. So as this is two-phase problem, viscosities are different. So this shell balance will be different for phase 1 and shell balance will be different for phase 2. Now integrating this equation, so what I will be getting? This tau xz will be equals to delta p divided by Lx into C1 for phase 1, and this will be C1 for phase 2. This is, say, you can write C1 and C2, no problem. C1, say any one, this is constant 1, this is constant, another constant. Okay, this is C1, this is C2. Okay, for phase 1, this is for phase 1, this is for phase 2. So you can write anything, any constant. Now whether, how to use, now you can use, so among these 4 boundary condition, there is only one flux boundary condition. So I can use this flux boundary condition at x equals to 0, tau zx for phase 1 will be equals to tau z, xz, not zx, xz for phase 1 will be equals to tau xz for phase 2. So you can use this boundary condition here and get the value of C1 for phase 1, or you can eliminate either one. Because I have only one boundary condition, so you can eliminate one constant from these two constant. Instead of two constant, one constant will remain this, because I need a two flux boundary condition. To eliminate two constant, I will be needing two boundary condition. But as I have only one boundary condition, so I can eliminate one constant from these two constant in a equation, flux profile equation. So what is that? So integrating this equation and using the boundary condition at x equals to 0. So at this interface, there will be a continuity of the fluxes. This is modified no slip boundary condition. So which constant? So what you will get, actually substitute in this equation at x equals to 0. So at x equals to 0. So at x equals to 0. So this will be equals to 0. This will be equals to 0. And tau xz1 will be equals to tau xz. Both equations are same. This will be equals to this. So it will give me C1 for phase 1 will be equals to C1 for phase 2. This is clear to you? Very simple. So at x equals to 0, substituting this here. So what you will get? So at x equals to 0, tau xz1 will be equals to tau xz2. So what you will get? C1 for phase 1 will be equals to C1 for phase 2. And substituting this, you can eliminate one constant. So that can be C1. C1 for phase 1 will be equals to C1 for phase 2. That will be equals to C1. So now one constant is eliminated using one boundary condition. Now I don't have second boundary condition for the flux. So I don't have second boundary condition for the flux. What is next step then? Roll number 18, Ashish.
Yes, sir. Hello.
So what is next step? Whether you have any other flux boundary condition?
No, sir.
So what can be done next step? Generalized method.
Sir, then we can write tau xz as minus mu dvz by dx, like for velocity.
Okay, what is the name of that law?
Sir, Newton's law of viscosity.
Very good. So introduce Newton's law of viscosity and get the differential equation for velocity, and integrate that equation and get the profile equation for velocity, which will have three constant, and I have three velocity boundary condition. Okay,
Yes.
now introduce here for phase 1 Newton's law of viscosity mu1, which will be relating with the gradient of velocity, and for phase 2 write Newton's law of viscosity where mu2 is relating with the gradient of velocity for phase 2. Okay, substitute Newton's law of viscosity and integrate the equation. Here, roll number 26, Vijit. I'm not able to hear you, Vijit. Roll number 35, Pranit. Yeah.
Sir, like, can you repeat question?
Repeat the question. What is the velocity profile? Don't estimate the constant with constant. How to get velocity profile? First of all, tell me, Pranit.
Newton's law of viscosity we can apply.
So just substituting Newton's law of viscosity, will get a velocity profile.
First, we have to find these constants.
No. What is velocity profile with constant? How to get a, after substituting Newton's law of viscosity, what we need to do?
We have to integrate, sir.
Very good. We need to integrate, and we will have one more constant, C2. C2 for
Yes,
phase 1 and C2 for phase 2. So with C1 and C2, what will be the velocity profile? Yeah, Praneeth, can you switch on your video?
Yes, sir.
Just show me your notes.
So like I'm not writing live notes.
Okay. So whatever you are writing, just tell me. Show me just whatever you are doing. Or you are not doing anything.
Listening to class only, sir.
Okay, very good. You are so clever.
So like after class, I do everything on my own. Like I will try on my own.
Okay, can you show me yesterday's class notes?
I haven't done yesterday's ones.
Okay, can you show me say class notes which we have taken a class on say
Yes, yeah, sure.
31st of January?
Hmm.
31st of January. What we got?
31st. Let me see dates. Like I'm not noting dates, but it's up to class 22, class 19.
Okay. Okay. Come to this class. What was the question?
Sir?
What was the question and what is your answer? What is velocity profile?
For this one. Wait.
Velocity profile for phase 1 equals to. Anybody got this velocity profile?
Hello, sir.
Yeah.
So for phase 1, it will be Vz equals to P naught minus PL upon 2 mu L, where mu 1 for phase 1, x square plus C1 by mu 1 x plus C2.
Very good. And similarly for phase 2 also, only constant will change. Okay.
Yes, sir.
Now substituting this in this equation. So this is a Newton's law of viscosity for phase 1. This is Newton's law of viscosity for phase 2. Substitute it here. This substitute this here. Okay. Substitute this equation in this equation. So what you will get? This is what you will get, minus mu1 dvz by d1. So and this is delta p. Integrating this equation, so this is what you will get, delta p divided by L 2 mu 1 L x square minus C1. This minus sign is coming in here. Okay, here also this minus sign is coming in here. Mu 1x plus C2 for phase 1. Similarly, velocity for phase 2 will be equals to minus delta p divided by 2 mu 2 L x square minus C1 for phase 2 x, and you need to remember that, okay, this is for phase 1. So this equation is valid only from x equals to minus b to x equals to 0. Okay, this equation is valid. This equation is valid for phase 2. Where is my phase 2? Phase 2 is from x equals to minus b to x equals to 0. And this equation is valid for x equals to 0 to x equals to plus b. Okay, now here I have two constants. One constant is C1, another constant is C2 for phase 1, and another constant is C2 for phase 3, and I have three velocity conditions. What are these three velocity conditions? Already we have seen at x equals to 0, there is a continuity of velocity. At x equals to minus b, of phase 1 velocity is 0 here, and at x equals to plus b, a velocity for phase 2 equals to 0. Substitute three boundary condition in these two equations. Three constants are there, so three boundary conditions are there. So I can estimate these three constants. Okay, I can estimate these three constants. So these three constants can be estimated, and you can get the velocity profile equation. First, you can substitute at x equals to 0. So at x equals to 0, if you put x equals to 0 here, x equals to 0 here, so this is 0. So V1Z will be equals to C2 for phase 1. And at x equals to 0 here, x equals to 0, V2 for phase 2, Vz for phase 2 will be equals to C2 for phase 2. And at x equals to 0, this equals to this. It means that C1 for phase 1 will be equals to C1 for phase 2. One constant is eliminated. Okay. Now substituting this boundary condition, what you will get? C1 for phase 1 will be equals to C2 for phase 2. Eliminating one constant. Okay. So eliminating one constant. So I'm substituting boundary condition number 3. So at x equals to minus b, at x equals to minus b, this v z for phase 1 equals to 0. This is x equals to minus b, substituting here. So you can see this sign is changed, and this is at x equals to plus b. Now you can combine this, substitute this C2 here, C2 for phase 1, and get the value of C1 and C2. Get the value of C1 and C2, substitute C1 and C2, and rearrange the equation. Rearrange the equation and get the velocity profile for phase 1, get the velocity profile for phase 2. And once you have C1, you can get the flux profile for phase 1 and flux profile for phase 2. It is observed that flux profile is same for phase 1 and phase 2. But velocity profile are different, because here you can see viscosity is the property which is differentiating two phases, and viscosity is playing role when I am moving from velocity flux to velocity. Okay, flux and velocity are related with the viscosity. Get the value of C1 and C2. Get the value of C1, C2 and substitute in this equation and get the, so get the value of C1, C2, this says C2, C2 and substitute here C1 and C2 and get velocity profile for phase 1 and velocity profile for phase 2. So anybody got C1 value? Very good. Substitute C1 and C2 and get the velocity profile equation. Okay. Okay, substitute C1 and C2 and get the velocity profile equation. This is C1 and this is C2. Everything is mathematics actually. So everything is mathematics. This is C1 and this is C2. Substitute this C1 and C2, you will get a velocity profile. Using this C1, you will get a flux profile. So you can get a flux profile. Substituting the value of C1 here, you will get a flux profile. So you can see after substituting C1 here, you get same flux profile. This flux profile is valid from -B to +B. Okay. So you can get back your boundary condition also. So at x equals to 0. So this is same actually. You will get same value for mu1 and mu2 at x equals to 0. Because at x equals to 0, this doesn't have any role to play. Then if you are moving in positive x or negative x, then this magnitude is changing, then flux are different. So this is my flux profile. Anybody not getting this flux profile? Hope everybody got this C1 correct. This is C2 and this is my flux profile. Substitute this value of C1 here and rearrange the equation. So this will be my flux profile. Okay. And then after substituting, and this is a velocity profile. If you substitute this velocity profile here, so velocity profile will be different. Okay, so this is the term which is differentiating actually. Okay, this mu2, because of mu2 and mu1, so it is velocities are different. So this velocity profile is valid for x equals to -b to 0, which will give you velocity profile for phase 1, and this is valid for x equals to 0 to +b. Why this is so? Because we have selected the origin at the center. Now, as I told, if you select the origin at the upper corner or lower corner, you will get different velocity profile, different flux profile. But absolute value of flux and velocity profile will remain same. Just check if you are getting this velocity profile. Anybody got this velocity profile? Aditya, you got velocity profile or flux profile?
Sir, I got flux profile and calculating velocity profile.
Okay, okay. Rutuja, you got velocity profile or flux profile?
Both profiles, sir.
Okay, okay. And you understood that flux profile is same
Yes, sir.
for both the phases, because viscosity is a property which is playing role. Differentiate two phases in momentum transfer and till flux. So viscosity has similar role to play actually. A similar role to play. Then when viscosity is relating flux with the velocity, that time it will be different actually. It will be different. So that is why you will get a different velocity profile for phase 1, which is valid from minus b to 0, and this is different velocity for phase 2, which is valid for 0 to plus b. So this is just mathematics. So you can just now you can get where will be maximum velocity. Maximum velocity will be there where gradient of velocity will be equals to 0. Okay. First of all, you need to decide mu1 is less than mu2 or mu2 is less than mu1. Okay, this is true for both. So it is, we have not assumed that mu1 is greater than mu1 or mu2 is greater than mu2. First, you need to decide whether mu1 is greater than mu2. If mu1 is greater than mu2, then differentiate this equation. If mu1 is greater than mu2 means maximum velocity will be in phase 2, and differentiate this velocity with respect to x and equate equals to 0, there you will get maximum velocity. If mu1 is less than mu2, okay, mu1 is less than mu2, then differentiate this equation. Differentiate this equation with respect to x and equate with equals to 0, and then there you will get a maximum velocity front. Okay, a zero flux condition. So that zero flux condition can be phase 1 or phase 2, anywhere. It can be anywhere. It all depends upon value of mu1 and mu2. So this equation of also, if you observe, if mu1 is greater than mu2, if mu1 is greater than mu2, then maximum velocity will be in phase 1 or x equals to b, and mu2 or mu1 is less than mu2, and maximum zero flux will be less than 0. B should be negative. There I will get this tau xz equals to 0. Okay, this is how you will get the average velocity. This average velocity, this is for phase 1. This is for phase 1. This is velocity 1 multiplied by surface area divided by surface area. But as it is not changing in which surface area perpendicular to flow. W width remains same. So divided by area, so here also width will come, here also width will come. So width got cancelled. So it is kind of 1 upon b minus b to 0 vz dx. So this will give you average velocity of phase 1, and this will give you average velocity of phase 2. This will give you average velocity for phase 2. Whether this average velocity is same or different. Whether this average velocity will be same or different. Roll number 35, Pranit. Pranit.
Yes, sir.
Whether this average velocity will be same or different for phase 1 and phase 2.
Average velocity,
Average velocity.
like it's not same. If mu1 and mu, like both viscosities are same, then only it will be same.
Very good. Average velocities will be different. Okay, average velocities will be different, but volumetric flow rate is adjusted such that interface is at center. Okay, the fluid which is having lesser viscosity will have average velocity more. Okay, fluid which is having lesser viscosity will have average velocity more, and fluid which is having more viscosity will have average velocity lesser. Okay. This will be the average velocity. This is average velocity. If you integrate over minus b to 0, v1z, and this will be the average velocity for phase 1, this will be the average velocity for phase 2. So you can see this is 7 mu1 plus mu2, and this is mu1 plus 7 mu2. If mu1 equals to mu2, then average velocities are same. So now you can calculate volumetric flow rate, you can calculate mass flow rate. How to calculate mass flow rate using average velocity? Roll number 45. Prabodh,
Yes, sir.
how to calculate mass flow rate?
So multiply by area and the density.
Okay, for phase 1, what will be the mass flow rate?
So rho1, rho1 into the average velocity, Vz1, multiplied by the area, which would be W into W into B. W into B.
Very good. It will not be 2b, it will be b. Because cross-sectional available for flow area for phase 1 is a b only. Thickness of film phase 1 is b and thickness of phase 2 is b. So it will be W into b into average velocity into density, that will give you mass flow rate. So now you can calculate drag force also. So how to calculate drag force? Roll number 53, Shivam.
Hello.
What will be the drag force exerted by flowing fluid on an upper plate?
Yes, sir. So the drag force will be uh, VZ1. VZ1. Yes, sir. At sorry,
Upper plate.
Upper plate means x equal to b, right? Over there, right? So sir, tau. I guess it will be tau 1. No, so tau 2. Upper plate tau 2 into area. So area will be
tau 2
into area of the like b into w.
So where you will estimate this tau 2?
At x equal to b.
Okay, so estimate tau at x equals to b. So given all these mu1 and mu2 and delta p, and this is dimension, slit, width of the slit and length of the slit. So you can estimate tau xz at x equals to b.
Yes, sir.
Multiplied by which surface area?
Into the area. Into like it will be x. Just a second. It will be w like width into the L like
Very good. It will be that perpendicular area to this momentum flux is a surface area of that plate. Okay?
Yes, sir.
W into L. And what will be the drag force exerted by flowing fluid on a bottom plate?
Into the bottom plate, it will be tau xz phase 2, like x equal to minus b
Very good.
in this equation
So you
into
just
area.
substitute x equals to minus b multiplied by W into
L.
W into L. So that will give you a drag force exerted by flowing fluid on a lower plate. Okay. So anybody has any doubt in this shell momentum balance approach? Any doubt? So this is what we are going to cover in a class, shell momentum balance approach. And in next class, we will have just a practice problem, couple of practice problem, and this will be the syllabus for midterm exam. So at home, you need to solve this problem. Just you need to solve all the problems given in chapter 2, but these are some important problem 2A.1 to 2A.4. These are the 4 problem and 12 problem from section B. These are important and easy problem. Okay, unsolved problem from chapter 2. Okay, these are easy problem. Other problems are also important. You try to solve all the problems, and this will be the syllabus for midterm exam. So whatever we have covered in a class, so we have not covered estimation of heat transfer coefficient, mass transfer coefficient, and momentum transfer coefficient other than flow or flat plate. That will not be there in examination. Okay, the estimation of heat transfer coefficient, mass transfer coefficient, and momentum transfer coefficient over a flat plate will be there in examination. Yeah, roll number 88.
Yes, sir.
88 is there.
Yes, sir.
Okay, it is clear. So we have covered flow over flat plate, estimation of heat transfer coefficient, mass transfer coefficient, and momentum transfer coefficient. That will be there in examination, but other we have not covered in a class. That will
Yes, sir.
not be there in this examination. Okay. So
Yes.
whatever we have covered in a class till now will be there for midterm examination.
Okay,
So
sir.
roll number 88, 94 is there, na? Your CR.
Yes, sir. Saransh.
Saransh, it is clear to you?
Yes, sir.
Roll number 75.
Yes, sir.
Okay, so whatever covered in the class, in next class we have one more class. Monday I will be taking class which will be based on shell balance approach only. So I don't want to start a new topic. It will be just a practice problem. Some of the practice problem, maybe from this unsolved problem, I will consider a couple of problems. And this is say you can take this as a take home assignment. Okay, you can take this as a take home assignment, and not compulsory to submit this assignment. I will think after examination whether this assignment I will ask you to submit or not. This is take home assignment. If you want to solve, you solve. If you don't want to solve, don't solve. If you want to improve the understanding and want to understand this transport phenomena well, these problems are very, very important. So you can solve all unsolved problem in problem chapter number 2. And now, based on whatever fundamentals we have discussed in related to shell balance approach, you can solve all the problems to get the velocity profile for laminar flow at least. So now you should be expert in what? When you have only one component of velocity and varying only in one direction, you should be able to solve the problem. Any problem, given any problem, you should be able to solve. If you have only one component of velocity and it is varying only in one direction, it can be for cylindrical, it can be for Cartesian, it can be for spherical, anything. One velocity component and changing in only one direction. Okay. So this is all about what I'm going to cover in today's class. If you have any doubt, anything related to shell balance or whatever we have covered till now, from say class number 1 to today's say 20 class, 25 classes, whatever we have covered, if you have any doubt, you can ask now also, or you can revise everything maybe today and tomorrow, and you can ask your doubt in Monday's class. Okay, whatever doubt, so that we can take it as a doubt clearing session and the practice session, doubt clearing and practice class on Monday. Okay, so we'll see. I will see. Okay, whether some problem from examination I will consider for discussion, or some problem from this unsolved section in transport phenomena BSL book I will consider. Anything we will consider as per demand. So whatever problem you want to discuss, just let me know. That problem we will discuss. Okay, then thank you very much.
Excuse me, sir.
Your roll number?
102.
102. Yeah, tell me.
Sir, I don't have any doubt regarding shell balance, but sir, immiscibility depends on viscosity only or density also?
It is based on density only.
Sir, we'll need to consider viscosity and density both now.
No, it is not viscosity, it is density and a polarity of the compound. If you go in thermodynamics, polarity is also playing a role considering immiscible fluid. If polarity is same, like for example, hexane and oil is having same polarity. Okay, oil is non-polar while water is highly polar. Hence they are immiscible, but nothing to do with viscosity.
Okay, sir, got it.
Okay, first of all, it will be immiscible based on polarity. Then there will be clear separation based on density. If density are different, then there will be clear separation. Otherwise, if polarity is different and density is same, you will get a bulk of phase 1, bulk of phase 2 moving here and there. It will not be completely miscible, but a group of molecules will be moving here and there. Like emulsion you have heard of, na?
Yes, sir.
Emulsion, so it will be a small concentration of oil in water, but it cannot be separated so easily, because even though polarity of water and oil is so different, but you will have fine droplets of oil moving here and there in water, but they are immiscible. They are not completely miscible. You cannot say that is miscible, but some kind of intermediate stage between miscible and immiscible emulsion. Polarity is playing a role. Viscosity doesn't have any role to play.
Okay, sir. Thank you.
Hello, sir.
Yeah. Roll number?
Sir, 85, Karthik.
Karthik, tell me.
Sir, initially in today's lecture, we saw that density cannot be always considered for viscosity, for accounting for viscosity.
Yeah, but roughly you have a relation actually. Rough relation you have.
Yes, sir. That's what I was asking. For a given flow, if we have Reynolds number, so can we account like density is directly proportional to viscosity?
No. Don't take that for granted actually. There are exceptions, and exceptions are well used in chemical engineering. Okay. So you are dealing
yes, sir.
with petroleum crudes and all, and then you are dealing with water. Okay, so exceptions are there, and these are well used. So don't remember that actually. Density relation between density and viscosity. Roughly you can have correlation, but as we have taken dilational constant, because that is not used in chemical engineering at all. So hence we are neglecting dilational constant. Similarly, on same line, you don't remember that relation density and viscosity. Okay?
Sir, and one more, that at the interface of two liquids, the velocity should be same. So one liquid is flowing faster due to less viscosity and another is slower. So at the interface,
At
what
interface, so I'm saying last layer of first fluid and first layer of second fluid.
Yes, sir.
That is
So
one layer.
okay.
That is one layer. Okay. At interface, that is just a theoretical separation. Whether you can have so clear separation between phase 1 and phase 2, it is not at all possible.
Yes,
okay, phase 1 and phase 2 will be considered as a one phase at interface. Interface, it will be interface equals to, that is last layer of first fluid, and that will be equals to first layer of second fluid.
Yes, sir.
Okay.
Yes.
So there will be continuity. There will be continuity of the velocity. The velocity equation will not be discontinuous.
Okay, sir. I thought that at the interface there would be some other velocity, like average of both or something like that.
No, because That is what the thing is. Then the interface, it is not so easy to study and model into equation. So these are all assumptions. So I am consuming interface, but at interface there are, because one molecule is having different force of attraction, second molecule is having different force of attraction, one molecule is having different density, viscosities are different, so many are different. But at interface, I am saying that, okay, this is interface equals to last layer of first fluid, and that is equals to first layer of second fluid.
Yes, sir.